time t belongs to the instance r plus, where u vanishes on the boundary of the omega and u at u of 0 is what you call the function u naught actually from some suitable space. I can say that omega is, you can call it, it's some domain in Rn actually. In Rn where n is less than or equal to 3. Okay? So this is what the problem that we are interested in. We want to show that the solution of this problem, when you take your initial data from a bounded sets, in other words, if you allow your initial data to vary within a bounded set, then the solution of this problem are going to stay in long run in a ball of certain radius actually. Or in other words, they will be absorbed by a ball of certain radius. So you have an absorbing set. If you have an absorbing set, you have the global attractor for this problem actually. So let's call this problem star. By the way, we have talked about in really detail, okay, so let's call this entire problem called star. We know about this problem that there exists, from our previous discussion, there exists a unique global solution of a star, okay, and we also proved in our classes that some regularity result, and we also show in our previous 2 lectures actually that if the condition, if the initial data is fixed, okay, so if the initial data are fixed, then the solution, okay, to this problem will converge to the stationary solution of the same problem actually, as t goes to infinity, as t goes to infinity. And we also showed, okay, in one of our previous lecture, that this problem is basically a gradient flow problem actually. In other words, its solution, the solution flows of this problem is basically a gradient flow actually. Okay, so we have also proved that, you know, that's a gradient flow. So if it is a gradient flow, if you want to prove, say, the existence of the global attractor, you don't have to prove the condition number 2 of the theorem that we just proved actually. That was the theorem about the sufficient condition of the existence of the global attractor, in which there were 2 conditions. Okay, so you don't have to worry about second condition because, you know, that's a gradient flow, and then for the gradient flow the second condition is satisfied. So you just have to worry about the absorbing set actually. Okay, this is what we have to do. So let me precisely state what I would like to do, and then let's talk about a quick strategy of proving the theorem. So the theorem that I am now interested in proving is that if you take the H to be H2 intersection H1 naught, okay, then this problem star as a global attractor actually, as a global attractor. So what do you mean by that? All bounded sets, or any bounded set of initial condition, will be attracted by the global attractor actually. Okay, it will be attracted by the global attractor. And what would be our strategy to prove? Okay, our strategy to prove is to use the theorem that we just proved actually about that was a sufficient condition for the existence of the global attractor. Okay, So strategy. So we will prove global existence, okay, through the last sufficient condition, last proved theorem, okay. So step 1, since star is gradient flow, so the condition 2 of, I don't know, condition 2 of last theorem is satisfied. Okay, so that means that you have to just focus on the existence of absorbing set actually. Okay, so we will show that there exists an absorbing set, okay, for U, where U is the solution of a star, okay, for solution U of a star, okay, this is what that is in H2, in H and hence in H2. And how we're going to show it? We're going to show that the H2 norm of the U, H2 norm of the U. In other words, we will prove that there exists an instant, say T0, such that after this instant T0, the H2 norm of the trajectories of the solution lives in a ball of radius of some constant actually. Okay, radius of some constant. Now one can say that basically we already have proved such results previously. Okay, in our previous 2 lectures, or when we studied, for example, this problem in detail, we already proved such result actually. So why we are again doing it? The key difference is that in previous estimates, when you estimated this by a constant, the constants were depending, so previously these constants were depending on the norms of the initial data actually. Okay, they were depending on the norm of the initial data, and hence the C were depending on the points. But now we are not interested in the fixed points, but we are interested in the bounded chunks of this set actually, the bounded set of initial condition. So your constant, which can play kind of the role of the radius in which the trajectory of the solution live, this constant should not depend on any specific initial condition. It may depend on the entire bounded set, but it should not depend on the initial condition actually. Okay, initial condition. So let's do it. Okay, let's do it actually. We're going to show there exists a constant C depending on the bounded set B of initial condition such that the H2 norm of the solution will be always less than or equal to this constant which depends on the bounded set B actually. Okay. And so this constant can be treated as the radius of the ball, in which once u enters after the instant t, it never leaves that ball actually. So you're going to call that ball is really an absorbing set for u. And if you have absorbing set, then the theorem that we proved just, you're going to have the existence of the global attractor actually. Because the condition 2 is already satisfied, the condition 1 will be, will be also true actually. So this is what that we would like to show. How are we going to show it? Okay, let me just show that how we will reach to this conclusion. So what we will try to do actually, so really the first step would be, to study some kind of energy of the problem star actually, and prove that its energy satisfies this kind of inequality, differential inequality. Okay, C1 T of t less than or equal to C1 T of t less than or equal to C2 for all t bigger than or equal to 0. So this is what something that we would like to show. Again, the constant C1 and C2, they don't depend on initial condition, they must depend on the bounded set B actually. Okay? For a given bounded set B in H, we would like to prove such differential inequality. Because once you have such differential inequality, you will have a solution of this form. Okay, so the step 2 would be, and so you're going to say that you're going to have the solution of this inequality that would look like something like this. Okay, e of 0 e to the minus c1 t plus c2 upon c1 actually. Okay, so it's going to be something solution like that. Now, if we choose B in such a way, okay, so if we choose okay, so if we choose B in such a way that this E of 0 can be estimated, for example, a constant C3, okay, which depends on B. Okay, so if you choose the bounded set B such that the E of 0 is less than or equal to some constant C3 depending on B, then obviously the E of t would be less than or equal to C3 e to the minus C1t plus C2 over C1. But from this description where you replace, for example, C3, we will try to find a constant C that depends on what do you call B, and that is an upper bound for E of t for all instants t actually. Okay? For all, not for all instants t, but for the instants t1. Okay? Some instant t1, which we'll later talk about that. Okay, what should be this t1 actually? That after the time t1, the energy of the system star enters into a ball of the radius c, and from this we will try to deduce this inequality. Okay, we will try to deduce this inequality, which we will show that the solution, the H2 norm of the solution is less than or equal to a constant depending on B actually, and hence we can say that after this instant T0 or T1, okay, some suitable instant, the trajectories of the solution, the H2 norm of the trajectories of the solution enter into the radius of ball C. So this is what really is going to be, so rather than giving step 1, I gave you almost all the steps actually. So this is what that we like to do. We like to first prove a differential inequality, solve it, then choose initial conditions from B such that the E of 0 depends on some constant, and from this we will deduce that the E of t would be less than or equal to some constant depending on B, or it will enter into a ball of the radius C, and from this we will deduce the inequality that we will want actually. Okay, so this is what is really the step-by-step way we're gonna go. So let's go. Let's start with the equation that we are interested in. So PDE plus U minus UQ. Okay. So the first step is, for example, multiply this equation UT throughout by U and integrate with respect to the space variable. So in other words, take the inner product of UT with U plus U plus UU minus UU cubed. Okay, this is what that you're going to get. By the way, whenever I will write inner product, this would be inner product in L2. Whenever I'm writing only norm, this would be norm in concrete situation L2. And if I have to say the norm in H, I will write explicitly H or H2 actually. Okay? But if I'm not writing anything, you have to assume that this is the norm in L2. And the inner product is also in L2 actually. Okay? So, we have done several times such calculation. I can rewrite this as 1 over 2. I can pull this time derivative out. The penalty would be to multiply 1 by 2, and you're going to have the inner product of U with U, and so this is going to be the norm of U square equal to, here I can apply the integration by parts. Okay, so it's an elliptic operator, so I can apply integration by parts. This will become negative gradient U, so it's going to be negative gradient U norm square, plus this will become norm of U square, okay, and this will become what? I can write that this will become that this is the integral of say U power 4, okay, U power 4 and dx actually. Okay, U power 4 and dx. This is what that you're going to get. I can rewrite this as 1 over 2 d by dt of norm of U square plus the gradient of U square plus the integral U power 4 dx. Okay, and this is equal to norm of U square actually. Okay. Now if I take this norm of U square, write this norm of U square explicitly, this is going to be U square dx over the integral omega. On integrand, if I say apply the Young's inequality, okay, so this inequality a power p by p plus b power q by q, where 1 over p plus 1 over q is equal to 1, the Young's inequality, and b are non-negative numbers. By taking a to be u square and b to be 1 and p and q to be 2 actually, okay, so if I take p and q to be 2, then this integrand, you can estimate this by the integral of, this is going to be u power 4 by 4, u power 4 by 2 plus, okay, plus 1, okay, plus 1 by 2 and dx. Okay, so this integral can be estimated by this, in which you can explicitly write that this is going to be 1/2 u power 4 dx plus the integral of 1/2. You can also write that, okay, this is the measure of the domain omega divided by 2. You can write it in this manner. So what did you get? You get that this side is less than or equal to this side actually. So what can be done? I can take, for example, this 1/2 u power 4, the integral of 1/2 u power 4 on the other side, and here I have 1, so it's going to remain with 1/2. So let's do this. So multiply this inequality throughout by 2 and subtract this term from this term. Okay, so when you're going to do it, what you're going to get? d by dt norm of u square plus 2 gradient of u square plus, this is going to be 2 minus 1, so this is going to be u power 4 dx over omega less than or equal to this constant actually, multiplied by 2, so it's going to be the domain of the omega actually. So this would be less than or equal to the constant c. Okay, so keep in view this constant does not depend on initial condition actually. So it's going to be less than or equal to this constant c. So let's call this equation number 1. Let's do another thing. Now let's repeat this step same and try to reach to another inequality. But this time I'm not going to multiply this with u throughout by u, but I'm going to multiply with the time derivative and then integrate with respect to the space variable actually. Okay? So if I don't know, call this as some equation, so let's call it eta. Okay, I don't know. So if you multiply eta by ut and integrate with respect to x, what you're going to get? You're going to get the inner product of ut with ut. This will become Laplace u ut plus u ut minus u cube ut. So this is what that you're going to get. Now what would be the simplified form of these terms? Bear in mind we're going to reach to a differential inequality in some kind of energy depending on the norms of u. Okay. What would be this? You can write this as this is going to be the norm of ut square for sure. Okay. This I can do same. I can pull the time derivative, I multiply 1/2 in penalty and then apply the integration by parts. So this is going to be, so it's going to be 1/2 the time derivative multiplied by Laplace u and then Laplace u like this will become negative gradient of u squared. So in other words, the first term will become minus 1/2 d by dt of the gradient of u square actually. So now what will happen with this term? I can keep this term as it is and I can say that this will become 1/2 the integral of u multiplied by ut and dx. This is a negative term. I can pull the time derivative out and then I need to multiply by 1/4 as penalty, and you're going to have the u cube u, which is going to be, so the last term is going to be minus 1/4 d by dt of the integral of u power 4 dx. Okay? U power 4 dx. This is what that you're going to get. Now these negative terms, I can throw them on other side, and I'm gonna get norm of ut square plus, and put, for example, these together. So it's gonna be 1/2 d by dt of, say, integral of, you can write this as that this is going to be integral with respect to x of the gradient of u square, okay, plus this will become u power 4 divided by 2 and dx. Okay, this is what that it is going to be, and this is equal to this 1/2 u ut and dx. On this, I would like to again apply the Young's inequality, okay, with the same parameters, by taking a to be u and say b to be ut. Okay, this time I'm going to take a to be u and b to be ut, and p and q are going to be 1/2. P and q are going to be 2 actually. So this is less than or equal to, so this will become 1/2 of the integral of u square over 2 plus ut square over 2 and dx. This is what that you're going to get, and therefore, so the first term that will become, we have a 1/2 here, we don't need a 1/2, there is no going to be 1/2, because this is simply u ut, so it's really u multiplied by ut and integral with respect to x over the omega. So I can rewrite this, now I can say that the first term is really the 1/2 of the L2 norm of u, plus the second term is also 1/2 of the L2 norm of ut square actually. So you have this estimate. So now what can be done? Now this can be done, for example, that throughout this inequality, so the final inequality is that this guy is less than or equal to these guys. So if I multiply this inequality throughout by 2, and for example take this on this side, so it's going to be 2 norm of ut square, this 2 will go away, this will go away, this will go away. So 2 norm of ut square minus 1 norm of ut square, so you're going to remain with only ut square. So the final inequality that you're going to get, okay, after this basic analysis is really this. Okay, so the norm of ut square plus when you're going to multiply everything by 2, okay, multiply by 2, so you're going to get the integral of the gradient of u square plus u power 4 upon 2 dx, and this is less than or equal to norm of u square actually. Let's call this equation 2. Okay. And now if I add equation 1 and 2, so let's add equation 1 and 2. So once you're going to add equation 1 and 2, what you're going to get? Let's add equation inequality 1 and inequalities 2. So when you're going to add inequality 1 and 2, you can put these derivate terms together and rest of the term separately. So you're going to get